Welcome to this Videometer Academy video about the Transformation Builder. The Transformation Builder is part of the third training module and is one of the most used functions in the Videometer software. Before going into how to create transformations, we will briefly go through why transformations are such an important and powerful tool in the Videometer software and what a transformation is after all. After this brief introduction, we will look into the three most general transformations and show some use cases of how and when to apply them. These three methods being the NCDA, the N-Mahanolobis, and MNF. The Videometer Lab transformation function is created by the user with reference to one or more images. These transformation functions are cornerstones in many other Videometer Lab applications and functions, such as image segmentation and classification features for machine learning classification models. Therefore, being able to create precise and useful transformations are one of the most important skills to master if you want to be successful with your image analysis in the Videometer software. But what is a transformation then after all? The meaning lies in the name itself. A transformation function transforms your multispectral image into a new image. This transformation is done by different statistical methods, which reduces the dimensionality of your image. These methods being the NCDA, N-Mahanolobis, and MNF, as already mentioned. And by dimensionality reduction, we mean that the 19-banded image is transformed into a single-banded image. The different transformation methods we will be trying out in this video is 1. The NCDA, 2. The N-Mahanolobis, and 3. The MNF. These methods represent three different types of analysis, the most used one being the NCDA on the known versus known case. Deeper explanations for these different analysis types is the remaining content of the video. First up is the NCDA transformation. NCDA stands for Normalized Canonical Discriminant Analysis. It is the statistical method which can take high-dimensional data, in this case our multispectral images, and then when the user defines two classes by painting in the image that he/she wants to separate or discriminate between, this method finds a way to do this and maps the result into a one-dimensional image with only one band. Due to this discrimination between the known classes, we call this a known versus known case. Some example of two known classes could be foreground versus background, pure sample versus admixture, healthy versus unhealthy, or eventually any imaginable comparison that you can think of. Before we show how to do the transformation in the software, we will briefly go over the NCDA basics. As it is seen here in the slide, we have an image of some vegetables. In the image is painted two colors, red on the vegetable, which is the foreground, and green on the background. These painted regions are now our two defined and known classes. When the NCDA transformation is performed, the output is the bottom image. We have transformed the original 19-banded image into a single-banded one, and the only information in the output image is the amount of difference between the foreground and the background. The transformed image is displayed in the jet color scale, which goes from blue to red, with pixels values ranging from -2 to 2. To visually support this explanation, all the pixels in the transformed image are plotted in a histogram. From the histogram it is clear that the two classes are now distributions with centers around -1 and 1, and the threshold value for separating these two classes will be 0. This is indicated with a green line in the middle. The color bar, which corresponds to the pixel value range, is included to help visualize where the separation between the red and blue class happens. The NCDA transformation is extremely easy to apply and use, and all the technical talk about statistical methods you eventually won't have to think about. There are only a few basic but important rules, which we will get to. Now we will show how to practically create this transformation with the NCDA, and again use the vegetable image as an example. We start by painting the vegetables red, which then becomes the foreground. Here it is important to paint all the different colors and variation in the vegetables. It is not the amount of paint, but what you paint that eventually will determine the quality of your transformation. As it is seen in the video, we make sure to include all the different colored regions on the vegetables to represent all the variation present in the foreground class. And most importantly, we make sure not to include any of the background pixels in our foreground class. Painting the background will make the transformation perform poorly. Once we are done painting the foreground class, we select the green color and start painting the background. Here again, it is extremely important to include all color variation in the background class. This includes possible shadows caused by the vegetables and write reflections from the Petri dish. Now we open the Transformation Builder, click on the MSI in the top menu bar, and select Transformation Builder, and the window pops up. First select the NCDA in the drop-down menu, then make sure to select the correct image under Data Source, and tick off the colors you have used to define your two classes with. Then press Calculate and let your computer think for a short while. Press Quick Apply to see how your transformation turned out on the selected image. Here we then have our transformed image, and we can turn on the color bar to visualize the -2:2 scale. A line is drawn across the image and the profile tool is opened. Here we can see how the value 0 separates the vegetables in the foreground from the background. In the Transformation Builder window, the statistical information for the newly calculated transformation is given. In the scatter plot, you can see the loadings for the different wavelengths in the original image and how each of the bands contributes to the transformation function. In the eigenvalue bar plot, we see how well the distinction between the two classes is. In this case, the value is 30, which indicates a good separation. A general rule of thumb is that if the value is larger than 3, the spectral difference between the two defined classes is considered to be sufficient. Even though it is very easy to perform these transformations, it can go wrong, and you can end up limiting the quality of your transformation. This can, for example, happen due to sloppy painting. Your computer is eventually very dumb, and it only does what you tell it to do. So, if you by mistake paint some foreground into the background class, this will confuse the algorithm and result in a less precise classification. Because what you want to do is to maximize the color distance between the two classes, and this becomes increasingly more difficult the more wrongly painted pixels you include. We have included a small video example to give a visual illustration of how sloppy or unprecise painting might affect your transformation negatively. In this transformation, we want to separate the yellow pepper from the light brown cracks on it. We start by making the transformation with unprecise painting on the cracks. In the video is seen how the cracks are painted with a big brush and how a great number of yellow pixels are also included in the marking. Then the background, which is the yellow part of the pepper, is painted with the green layer. Now we create the transformation as we have just learned in the previous video example. In the transformed image, we surely enough see that the cracks are on the red class and the pepper the blue class. But there is a lot of green and yellowish area as well on the pepper, indicating that the transformation is quite unsure what to do with these parts of the image. We try to repaint the cracks a little bit more carefully with a smaller brush size, and then recalculate the transformation and see how this makes a difference. The brush size is now only 5 pixels, and the cracks are painted carefully with only small dots. The difference between the two transformed images is very big. The pepper is now the same homogeneous blue color, and the cracks clearly stand out, very well defined. The take-home message from this small example is that the precision of the painting eventually determines the quality of your transformation. Creating a good transformation is an iterative process. It takes a limited amount of time to paint a little bit more or a little bit different, and then recalculate the transformation to get a better result and verify it with a quick apply button. Next up is the n Mahalanobis transformation. N Mahalanobis stands for normalized Mahalanobis. A Mahalanobis distance is a measure of how far a point P is from a distribution of several points in standard deviations. This is all very mathematical, but essentially it is a metric for measuring distances or differences in data. By applying this Mahalanobis distance as a transformation, we can in the Videometer Lab software visualize how different a class is compared to everything else in the image. This is why we call this the known versus unknown case. We know how our defined class looks, hence called known, but not in what context or with what other objects or background we might be viewing it. Some example use cases could be foreground versus any imaginable background, anomality detection in a sample, or product in an unknown background. Before we show how to do the Mahalanobis transformation in the software, we will briefly go over the basics behind it. On the slide you see an image of some vegetables where the carrot has been painted with the blue class. We then create the n Mahalanobis transformation to measure how different the orange carrot is compared to the rest of the image. The transformed image is almost completely dark red except for the carrot. On the color bar, the scale goes from 0 to 3. These scales reflect the distance measured with respect to the caret. All in Mahalanobis transformations are created with this default scaling between 0 to 3 distances. When the distance is larger than 3 standard deviations, the differences are set to be large enough to make a confident separation from the reference class. But if you reset the scale, you will see how the image changes completely. The scale now goes from 0 to 21, indicating that the biggest color difference in the image is 21 standard deviations away from the caret. And this is the red part of the image, the broccoli, and the dark part of the avocado. Contrary to the NCDA transformation, where the scaling is always mapped to fit into the scale -2 to 2, the Mahalanobis scale could take 0 to incredibly high values if the object's image are spectrally very different. We will just include a small part on the heavier theoretical information on the standard deviation distance for those of you who are interested. So, the Mahalanobis distance is a weighted distance according to the covariance structure between classes. If you plot the different color classes of your objects in a coordinate system, as it is done in the slide, you will get some distribution which look like clouds. The distances between these color clouds are determined by the number of standard deviations from the reference class distribution. In this example, our red class is the caret, and the distance to the spinach leaf and the broccoli pixels are then determined by the distance to the mean value of the caret class, as it is shown in the plot. If you plot the caret values compared to the broccoli in the histogram, you will see how the two vegetables are different from each other by a large margin. If you then draw a line through the transformed image and plot a profile, you will see how it is possible to separate the caret from the rest of the image with a threshold value of 3. We will now show how to perform the Mahalanobis transformation on the same vegetable image in the Videometer Lab software. Start by painting your reference class and make sure to include all color variations within this class. Then select Mahalanobis from the drop-down menu and select the correct reference image together with the right color layer and press Calculate. Then do Quick Apply to see the result. We turn on the color bar and try to reset the scale. With this painting of the caret, the distance scale goes up to 26 standard deviations. For the Mahalanobis, it is possible to add several reference classes to the transformation. So, when you perform the transformation, the distance to all the pixels in the image will be the distance to the closest reference class. In the video here, the chickpeas are colored with the green layer and included in the transformation together with the caret. When we then apply the resulting transformation, we see that the distance to the garlic and the grape generally becomes smaller, as they are spectrally more similar to the chickpeas. Also, the maximum distance is now 8.2 standard deviation and not 26, as this newly introduced class spans more of the color space. We can keep adding more classes to the transformation, as it is seen done in the video. And every time we add a new class, we see how the dynamics in the transformed image change. One thing that can be realized from this is also, when we paint the green part of the avocado, the distance to the spinach doesn't seem to change, indicating that there are spectral differences between the 19 wavelengths capturing other details than just a green color. Now moving on to the last of the transformations, the unknown versus unknown case, the MNF transformation. MNF stands for minimum noise fraction. This transformation decorrelates and rescales the noise in the image data. When you perform the MNF on an image, the different noise profiles are visualized in an ordered fashion, having the same number of bands as the original image. We call this method for an unknown versus unknown case, as it is used for general exploratory analysis where no references are set and the transformation is calculated on the entire image. Examples for use cases are normally general exploratory analysis, where the goal is to detect anomalies in the image which are not immediately visible to the eye. Before showing how to perform the MNF transformation in the Videometer Lab software, we will just briefly show the basics on a couple of slides. As an example, we will use this image of a sugar sample with some admixture in it. When we perform the MNF, we get 19 bands in the output image, and the transformed image is still in grayscale as well. Here is seen a selection of 4 bands from the MNF transformation. In the first band, the primary feature visualized is the texture of the sample. In the second band, the defining feature might seem to be based on the composition of the sample, where we see some of the sugar grains standing out together with the admixture. In the fourth band, the admixture stands out clearly as the only feature, and in the sixth band, the noise has been reduced to simply white noise. The MNF works in similar fashion as PCA, and the later bands in the MNF transformed image will gradually become more noisy. The statistical information which shows up in the transformation below window after calculation is seen here in the slide. The component list to the left indicates how much of the variation in the image is explained by each of the 19 bands. In this sugar case, the first band expresses 66% of the variation, the second band 17%, and the third 12%, and so on. The middle plot displays the loading for each band over the different wavelengths. This is how important each wavelength is for the resulting MNF band. The eigenvalue histogram explains similar information as the component list, where the percentages instead are explained as eigenvalues. The MNF has also been applied to an image of skin, where the first 4 bands of the MNF transformation is displayed here in the slide. For each band, it is clear how different characteristics in the image stand out. To apply the MNF transformation in the software, select the MNF from the drop-down menu and select the correct image. Then select Full Image and press Calculate. Then press Apply to see the result. In the video you see how the level of noise in the image goes up as we go through the layers. In the final layers it is just pure white noise. Please note that it is also possible to base only the MNF calculation on the painted area, but afterwards apply it on the entire image. In the example with the skin, you see in the video how it is possible to select specific components or bands from the component list. When you do this and apply the transformation, the resulting image will only have the selected number of bands for these specific noise channels.